Is it audible?
Yes, sir.
Yes, sir.
So in the last class, we have discussed about the highlights of the ARM architecture. Then we started with the ARM architecture. So we called that as ARM instruction set architecture. Studied in detail about the different blocks, what is present inside the ARM7 architecture. And when we started studying about that in detail about the ARM architecture, we found that ARM7 supports a lot of operating modes to work its way. So those modes are the 7 modes. Any one of these modes, the controller or the core exists at any moment of time. So these modes are the supervisor mode to start with and reset. So then you switch to user mode where you run most of your application programs. So whenever you feel like running your kernel code, always you come back to the supervisor mode using SWO instructions and then go back to the user mode. Whenever you want to modify certain registers like control program status register, a privileged register, then you go back to the system mode, access that register, modify the contents of that, and then go back to the user mode. So microcontroller is always a device which can handle multiple things simultaneously. That is why it's called as a real-time system. So whenever you call such systems as a real-time system, you should be able to support what is called request coming from the different devices, either from the microcontroller inside the chip or from the external peripherals. So we divided all those peripherals into 2 types: the devices which requires the faster request, the devices which requires the normal request. So based on that, ARM core enters into the FIQ mode and to the IRQ mode. So whenever you're going to access memory which is not physically present in the chip, so then you have an abort exception. That means that you go to the routine where you do the how to handle that error is taken care. Whenever you are going to access a 32-bit number which is not a valid instruction, then undefined exception is going to generate. That means that at that time it branches the set of instructions where you're going to handle this error. So these are the 7 modes which are supported for the ARM architecture. So I've shown that when you run your program will be in any one of these modes only. So now we will go to the next part of the ARM architecture. That is also we have discussed in detail. So ARM architecture basically supports for a programmer, so 16 registers. We call it a general purpose registers. So those registers are called by the name R0 to R15. So R0 to R15 is the registers which are present so inside the microcontroller. These registers R0 to R15, so we have discussed that 3 has got a special function. It is left to the programmer whether use that function or you can use that as a general purpose register. Whereas a program counter is an essential, you cannot use as a general purpose register. So if you handle it, you lose the sequencing. So program counter R15. So R14 is as a link register, which reduces the time required by the ARM core whenever you are executing the procedures, implementing the procedure calls. Stack pointer is required when you are implementing highly nested program structures, or you want to push a lot of data into the stack and access them in the procedures. So if you leave R13 and R15, a programmer can access R0 to R12 registers. We also studied R0 is a 32-bit register because 32-bit microcontroller LPC2148 uses ARM7 core, which is 32-bit. But you should always remember that whenever your CPU is 32-bit, the registers also will be 32-bit. Or if you know that the registers inside GPR registers are 32-bit, you can immediately tell the CPU is 32-bit type. So that is a one way to identify whether it's a 32-bit chip or 32-bit microcontroller or 32-bit code or CPU code. Whenever you have a 32-bit space, you can store a 32-bit number. The numbers what they generally use in a program is two types of numbers are there. You would have seen in the C also. An integer can store a 32-bit number or an address. So when you declare as a pointer, you can store a number, 32-bit number, but that number is not a data. It is an address of a memory location. When you just generally declare integer a, you know that it is not an address, it is holding the data. Similarly here also, so there is no explicit declarations are there. That means that R0 is meant for address or pointer like that. R0, you can use it for storing the data or the memory address. So it's left to the programmer how he uses a register to implement his logics. So these 12 registers or 13 registers, R0 to 12, will be using in a program to implement different logics. Now, so we will understand some more about these registers with reference to modes. I said, whenever you are in the user and system mode, because user and system mode, I'll consider them as the same mode. There's no differences there. Hello, am I audible?
Yes, sir.
Yes, sir.
Yeah. So whenever you use 32-bit registers in a mode, there's some concepts you have to understand with reference to ARM architecture. This is one of the novelty or the new way of increasing the throughput into the system. So this is the first time ARM has introduced in the market when they release their chips. We will understand. It requires little understanding. So don't look at these blocks under FIQ, IRQ, SVC and defined abort. Just look at user. Now this is the register what we have seen here. So this is nothing but these are the registers what I have seen here in the user mode or system mode. Both are same, refer to the same thing. So these are the registers I'll be using in my program. As PC is a program counter, which I'm using to sequencing of the instructions. So Cpsr is a register which holds certain flags, certain important status information, which we study in detail. So which will be helpful for the programmer to look at this register whenever he writes the program. So these are the registers what is available. So look at only this one. Now, let's say now the programmer is executing a program. At that time, a request is generated by a peripheral which wants immediate service. So what you are doing, you are executing a program. So it is not completed. So a big program is there. So you are executing this program. So let's say somewhere you are here in the mid of a program. So these are the registers which are used in the program to implement this logic by the programmer. Now what will happen? Immediately, since it's a microcontroller, lot of devices request a service. So some device has raised the request. So then what you are doing? You are in this program. Now, since the request is very important, I have to stop my program at this point, and then I should branch and execute a program which is meant for servicing the device which has raised the request. So you are here in the user mode. A request is generated by device. Lot of peripheral sensors are there outside this one. Lot of peripherals are there outside the microcontroller. You supposed to attend that peripherals in an urgent mode, because the peripheral, if you don't accept the data coming from the sensor peripheral, you lose the data. Let's say a sensor generates some thousands of samples every microsecond or every millisecond or every second. So whenever it generates the data, you have to catch that data. You have to collect the data and put it inside the microcontroller memory. If I don't collect it, what will happen? That second you lose it. You go into what? Next second. So previous second data is lost. Same thing happens in the life also. So every moment is precious. When you live in the present moment, you can encash the maximum in this moment, because you can live, you can give your 100% only into the present moment. I cannot go back to the previous moment, a previous day. I can put an effort on that, or I cannot go to the future and put an effort. I can put only in the what? Present moment. So present moment is important in the life. That is why I generally say, don't worry about the past too much. Don't be anxious about the future. Live in the present moment. Was it useful? Your feedback. The idea is good?
Yes, sir.
Yeah. Yes. So similarly, microcontroller also. So when the sensors throws the data, you have to collect it. If you don't collect it, what will happen? You lose the data. Nothing happens to peripheral or send the sensors. Microcontroller loses the data. So that is why immediately it should stop this program here, go back to another program which is already written and kept in the microcontroller memory. What is the job of this program? Whenever request comes from a particular peripheral, so you have to execute this program. What the program will do? Collect the data from this peripheral, do some processing, put in the memory, or take certain action based on the data. So this is what already has been decided by the programmer and kept the program in the memory. So whenever you get a request from very important peripheral, then you go from user mode to FIQ mode. That's what we have discussed, the mode. The moment request comes here, microcontroller has been designed by the chip manufacturers already that it switches automatically into the FIQ mode. So whenever you go to the FIQ mode, always you have to remember that you are in the middle of some other program execution. All these registers, that is general purpose registers, are already used by the programmer to implement certain logics in this program based on his requirement. Some register may be using some data, some register may be used to keep some address, but everything is engaged. Now immediately you switch to FIQ, you are executing a different program. So these program logics are different, the methods are different, the way you use the registers are different. So if I try to use the same register set now, because only one register set is there, if I use it, what will happen? If I finish this and go back to this program back here, then what will happen? All the data which was important, intermediate values for that will be lost. So what should I do it? One method is take all these registers and push into the stack, that is a memory. So and then you can use these registers in this program. Once you finish, pop back all the data into these registers and leave the back to the place wherever it was executing. That I can do it. But the question is the time it takes to push all this data. So is a time constraint. So always when you get an interrupt, how fast you can switch to the program and start executing, that we call is a word called latency. So less the latency, it is better. That is, the more you take the time, the more you are losing data from the sensor. So that is why So ARM people thought that, the designers of an architecture thought that, how do we increase the efficiency or throughput, reduce this latency? So they thought that, let us provide another registered set called R02 or full register separate set. Physically they are different. So names are same, but physically there's a different. Because why? So you are not disturbing this one because you physically set is different, but R02 or names are same because name should be same for writing a programmer. Programmer cannot think differently when you write a different programs for either sensors or for general purpose programmer. For a programmer, always what he thinks, R02 or R15 is available for me for writing the program. That's all. Whether physically you provide other copy or the same copy, it does not matter. But it takes, they thought that implementing the registers inside the controllers or the core is very costly affair because it's a flip-flop. Every bit of implementation a flip-flop, you studied in the logic, digital electronics in the last semester. Every flip-flop requires so many gates, yes or no? So implementing one flip-flop is required for 1 bit of storage in a register. So that means that one flip-flop consumes a lot of money. So that is why registers, more the registers, the cost of the chips will be more, the size is more, the power consumption is more. That is why most of the microcontrollers, they provide only minimal set of registers. It is not like a memory because memory is outside. Space is not constrained. Power consumption is not a constraint. Money is not a constraint. Microcontroller what? Its cost is more. When the chip size increases, the overall cost of the microcontroller increases. They will keep minimal number of registers. So they thought that it is not possible to provide complete another physical set of register just for FIQ mode. So they say that they gone for a 50-50. 50-50 in sense, I cannot provide complete R012 replacement. Let me provide at least half of the registers so that 50-50, so that efficiency can improve by 50. So they have provided physically R8 to R14 another set of registers. That means physically they are different. What is indicated in the color, blue color, that means that physically they are different. That means that if you ask me the question, there are two R8 registers are there. One in the user mode, it's accessible to the programmer. Same R8 is there in the FIQ mode. If I refer R8 in the FIQ mode, you are referring to this physical register. If you refer to R8 in the user mode, you are referring to this physical space. There's only one R8 for a programmer available. But physically, there are two registers are there. Which is accessible to the programmer? That depends upon which mode you are there. Whether you are in the user mode or in the FIQ mode. So they have provided set of these registers, extra registers apart from these registers. What are registers? 8, 9, 10, 11, 12, 13 and the 14. So if I am going to use only these registers in my interrupt service routines or the programs meant for servicing the request, then actually you need not push these registers. Because why? Physically they are already different set. You need not require to push these contents of these registers. Because why? It's a different set. You can start writing the program. Once you finish and go back, you can just start executing this program because physically they are different. So now, totally how many registers? Till now we have understood R0 to R15, 16. So then one control register. So when I go to the FIQ mode, they provide physically extra set of registers. How many are there? 1, 2, 3, 4, 5, 6, 7. 7 extra registers. So 16 plus 7 we have understood now till now. As there is only one program counter. See, program counter meaning is what? Sequencing the program one after the other. The job of this program counter is same whether you are in the user mode, any mode. That is why, see, R15 is same in all the modes. See, it's an empty. It's an empty. That means that same R15 register which is used in the user mode as a program counter, the same register will be used as a program counter in all the modes because it's a common. Similarly, in case of, hello, am I audible?
Yes, sir.
Yeah. So Cpsr register, which is also same because which holds the status of the program, it should be the same. So they provided the same Cpsr in all the modes. Now I'm in the FIQ mode. I finished my program. I go back to the user mode. Now again you started executing this program from wherever you left. Now again you are somewhere in this part of your program. You came here. Again request came from another interrupt device, a sensor, which is not very urgent, but we say that you take the service. you give the service. That's what it's asking the microcontroller. So now you have to attend what is called IRQ mode. So there is another program is written and kept in the memory to do the service for this IRQ. So what you have to do is, again, you have to stop wherever there, go back and execute this program and do the service for this device which has rise through an IRQ request input. So now I am in this program. So same set of registers are available for me. So is any physically different? Come here. So look at this here. No, because there is no provision or no money to implement again separate set of registers. They said only R13 and 14 because the stack in a program, the stack of this main program is different. When you come here, again the stack of this program will be different. You're pushing and popping related to this program. When you come to here, the pushing and popping into the stack of this program will be different. So that is why each of the program may have a different stack. So they said that stack point and link register, let us give separately in every mode. At least the throughput is better if you don't provide these ones. So that means that what will happen? So whenever you get a request, only you push or take care of these registers. Don't worry about the SP and LR register. Go back to another program. Correct now. Use separate set of R13 and R14, which is meant for this program. And then once you finish, don't require to retrieve R13 and 14. You come back because R13 to 14 of this program is different. So only to increase the throughput to some extent, they provided a dedicated R13 and R14 in every mode. Now how many extra are there? So now 7 extra were there. 1, 2, 3, 4, 5, 6, 7, 8. So 8 plus 7. So that is 15. So 15 plus 16. 31 registers are there totally in the ARM7 architecture. So if somebody asks how many registers, 31 registers are there. 16, 7, 2, 2, 2, 2. 31 registers are there here. Now, apart from this, they have a register called these program status register. So look at these one register. That means that whenever you branch from the user mode to any of these modes, the Cpsr register which holds the flags, which indicates the status of the program, running program at any moment of time, which is a crucial, which is like a, it is like a, you're talking to somebody in the mobile, you're noting down something on the paper, you're in between the conversation, you noted down few numbers, something like that. Somebody called you. What you do immediately? You leave your the paper there. Now you engage in other discussion with another person. Again, the another person discussion requires some noting down. You cannot use the old paper because it's in between. Something you noted down, jolted down there. So immediately what happens? You pull another paper, note down what is required. Then once you finish this one, then you come back, use a old paper. Same thing is a Cpsr register. Cpsr is just an intermediate important information about your program. Carry flag, zero flag, overflow flag, all these information will be there. So whether you're in the thumb instruction mode, so many things will be stored here. So when I go back to other mode to execute other program relevant to some other service to the device, Cpsr content should not be disturbed. For that, they are provided in every mode to store the contents of Cpsr. So let's say I'll go to the FAQ mode, store it in the SPCR for a moment. Yes or no? Now use the Cpsr to store the new program relevance, that is status of the new program. Once you finish this one, copy this back SPCR into the Cpsr and then start executing the program wherever you left it. So then what will happen? The old contents, whatever you noted down in the Cpsr in the paper will be there, relevant there. So it is like this. So whenever you go to any mode, copy the SPSR into the SPSR of that mode, start using the Cpsr to represent the logic of this program. You finish, copy back the SPSR to the Cpsr and continue execution of the whole program. That is why separate SPSR is provided to enhance the throughput of your execution. If you don't provide, what happens? You have to push it to the flag, then use it, then pop it from the stack. Avoiding pushing into the stack and popping it wherever possible enhances the throughput or performance of the microcontroller. So that is why if somebody asks how many registers are there in ARM7 architecture, so physically different registers are there. So 16 plus 7 plus 2 plus 2 plus 2 plus 2. Hello, am I audible?
Yes, sir.
Yeah.
Yes, sir.
So totally 37 registers are there. So this is a general question, generally asked in the exam. Explain the register architecture of ARM7 architecture or ARM architecture. And what do you have to say? ARM architecture supports 37 registers which are distributed physically to support the different modes of operation. In the user and system mode, you have the 16 registers R0 to R15, and to support or to enhance approach another set of R8 to R14 registers only in FIQ mode, and to support or to enhance the throughput of the system, R13 to R14, R13 and 14 is physically present differently in all the different modes. R13, R14 exists separately in every mode, in 6 modes. So R13, 14 of user mode is different, 13, 14 of FIQ mode is different, 13, 14 of other modes are different. Similarly, to enhance the throughput, all the modes have a separate Cpsr register, program status register, which is used to hold the contents of Cpsr whenever it comes to the particular mode, and when it finishes that mode and go back to the user mode, Cpsr contents will be loaded back into the Cpsr registers. So this is how the working of different registers are there in case of a ARM7 architecture. So now we have studied about the different registers, what is present inside the ARM architecture. So now let's understand the working of Cpsr registers. So I have summarized here mode switching. So what is a mode switching? When the processor switches the mode, say from the user mode to FIQ mode, when the user mode to FIQ mode, some of the user mode registers are replaced by another set of registers. Here R8 to R14 are replaced by another set of registers, and the names of these registers are fixed by FIQ, like FIQ R14, FIQ R8, like that. That means that physically they are different. So now we will understand what is a Cpsr register. Cpsr register, current program status register, is very important register, and there's only one such register for the processor. The Cpsr contains the information about current state of the processor. What does it contain? It contains information about the current state of the processor. It has bits which specifies the mode, control bits to enable or disable FIQ, RIQ interrupts, thumb and arm mode in use, and the conditional flag sign overflow carry 0, meaning is same as that of 8086 and 8015. We will study that in detail now, one by one, what is available here. Now, this is the register, 32-bit register, which represent Cpsr register. Now, the Cpsr register, if you look at that, this 31 bits contains so much information. What are the information it contains? Which is very important for us is it contains the information called status information. Status information is very important, which is represented by the set of bits or set of flip-flops. Each flip-flop or each bit we call by flag. We use a word called as a flags. So these set of flags represent the status information of your program. So what are the flags which forms the status information? So one is the C, which represents the carry flag. We will understand what is the meaning of it. Then you have Z, which represents the 0 flag. So then we have the N, which represents the negative flag. So there is a sign flag we also call as. Then we have V, which is called as a overflow flag. So these are the 4 flags which represents information or status information of your program. Apart from these, there are other flags there which are called as control or status information, can be combined both. So those meanings are, the T is used to indicate whether ARM is in thumb mode or not. This is used to indicate ARM is thumb mode or 32-bit instruction mode. Then you have I and F, 2 flags there, which is used to control whether the interrupt system should work or not. I is used to enable normal interrupt requests or disable the normal interrupts. F is used to enable or disable the faster interrupt requests. That is, there is a facilities there inside the microcontroller to stop requesting the interrupt from the devices when it is required. When you are executing very important code, there is no way to stop the program. Otherwise, it will damage the execution logic. In such cases, you can always, programmer can stop it by setting these 2 bits. So 1 bit for disabling or enabling the normal interrupts. Other bit is disabling or enabling the FIQ interrupts. The T indicates when you are in the thumb mode or a normal 32-bit execution mode. The M0 to M4 indicate which is the operating mode. As I said, you have 7 operating modes there. Of course, they have provided more number of bits than required because to support the compatibility in the next ARM course. Many times what will happen when they design the code, they always keep in mind that they are going to design in the nearby future the other facilities or other features which is not there in this one. So the programs what is written in the lower architectures should be supported in the next architectures. To keep in mind that they always give certain bits, hoping that these bits may be used for the next architecture so that compatibility can be retained. That is why they provided M0 to M4 to different the operating modes. So what does have an operating modes? Like a user mode, supervisor mode, those modes. So summarizing, control and program status register contains the following information. Number 1, it contains the information about the status flags, which is nothing but set of 4 flags which are used in the execution implementation of the program. So these flags are sign flag, 0 flag, carry flag, and the overflow flag. This is status flags. Then it has 1 bit, second use of the Cpsr register. It has 1 bit which indicates it's in the thumb mode or a 32-bit execution mode. The third use of Cpsr register, it has got a 2 bits which is used to enable or disable the interrupt request, normal and faster interrupt request. Then the 4th use, it has a 5 bits which are dedicated in the Cpsr register, which indicates in which mode your CPU is in execution now, which mode it is there at present. So these are the 4 uses of the Cpsr register. It is a 32-bit register which is accessible in every mode. Only thing is user mode cannot modify these register. For example, you want to disable and enable the interrupts. It is better not to provide to the user programs because you may stop. He may misadvertently modify certain bits. So it's better give certain privilege. That is why system mode is provided. Switch the user mode to system mode and then modify them, come back to the user mode. So when this facility is there, user always thinks twice. Oh, I am changing this one. I am changing this one. So user mode, so that I am able to modifying this one. If you don't give this privilege, what will happen? You, without your knowledge, because of doing something else, you are accessing these bits. But at the process of accessing this one, you may modify these bits so that it stops the request on the interrupt itself. It's a catastrophic effect on the total system. Am I audible?
Yes, sir.
Hello, am I audible? Yeah. So this is the meaning of what is called Cpsr registers. So now we will go to the use of these flags. What are the meaning of each of the flags? What we use it. Whenever you write a program, for example, you add 2 numbers, you perform certain logical operations, you compare the 2 numbers. It's very important that you should look at the result of the operation. How do you look at the result of the operation? There are 2 ways to looking at the result of the operation. So one is you look at the result of the operation by looking at the answer. For example, if I add two numbers, R0 to R1, and keep the answer in R0 or R1. So what is the way of looking at your answer? He is looking at the answer in a register. Now let's understand that by going back to this program. So let's say this is a program. Now it's an empty, nothing is there in the program. Are you seeing the kill compiler? Hello?
Yes, sir.
Yeah. Let's say I'm going to add two numbers. Move R0, comma, let's say #5, move R1, comma, #6. Now I'm going to add the numbers at R2, comma, R1, comma, R0. Let's say this is a program I am adding. So now what I am doing is I'm adding these two programs and keeping this answer in an R2 register. Now I'll execute the program. Now I will execute the program. Now no errors are there. Now I'll run the program. Now look at the program running. So R0 is a 5 you have got. So then you have R1 is a 6, which is also there. Now I'm going to add this program is going to add 5 plus 6. Answer is 11, which is stored in hexadecimal, that is B, which is there in the R2 register once I finish this. So you got a B. So now I have executed a program successfully. Now I have got the answer in the B register. So what is an answer? Is a B is an answer. Now, if I ask you, what is an answer out of this instruction? You say, sir, B is an answer. But if you ask me, what is an answer? I'll say, answer is B plus there are certain 4 flags are there which has been set as per this data, as per your answer. That is my complete answer. That means that answer is not complete if you just say only R2. You have to say flags. Now, where is the flags? Which is a register which contains the flags? Cpsr is a register which contains the flags. So go here on the left side, expand the Cpsr. Look at that Cpsr. Cpsr contains 4 information. One is M. M is what? The mode in which it is there. That is, it indicates by 13, some number, which is represented by 5 bits. Then there are thumb, T is 0. That means that I am not in the thumb mode now. Then I and F represents enabling or disabling of the interrupts, which is 1. Interrupts are enabled. Now, the other last use of Cpsr is the flags. What are the flags? N, sign flag. So it represents if N is 1, that means the answer is negative. If N is 0, that means that answer is positive. That is the meaning of a sign flag, or it's called as a negative flag. 0 flag. If the answer is 0, this flag is 1. Indicate that you have produced a 0 answer. When the answer is not 0, it is 0. Similarly, carry flag. So as you would have studied in the digital electronics and computer organization, whenever you add the two numbers, whatever the carry generated from the last bit of a number is the carry. So that we hold in this flag to indicate what is a carry. Am I audible?
Yes, sir.
Yeah. So there is one more flag called overflow flag, which says that you produced an answer which cannot be held by the resultant register and you lost the meaning of the answer. So we will go in detail about these flags because these flags are crucial for assembly programmer to implement their logics. If you want to include if and else, if you want to use a for loops, so if you want to use a while condition, everything in lower level language is based on these flags only, 4 flags only. In a high level language, you need not worry because they already would have provided a construct called if, while, else, for. These constructs are provided by the compiler developers. That means already there. You have to put the logic here. In the low-level language, constructs are not there. You have to implement the constructs by yourself. That is why implementing or writing a program at low-level language is really challenging. Only a good programmers with a lot of understanding of architecture can write an assembly programs. Now, let's understand this one. Now, all these flags has not changed. All 00 is there, even though I added certain numbers. Why? Because I have not asked the instruction to produce the change in the flags. So in ARM instructions, there is a requirement is there. Whenever you write a program, you have to add an yes to the instruction. Say that suffix, that is change the status flags. When you add a suffix as a yes to instruction, then only the flags are going to be modified as per your result. If S is not added, result is produced in R2, but the flags are not going to change. That is why S suffix to be added to any of the data processing instructions whenever you want the flags to be changed as per your answer. Am I audible?
Yes, sir.
Okay. So now again, I compile my program. I compile my program. I run the program again. Now look at the flags now. So now these many flags are there. So 1, 2, 3, 4. So answer may change and may not change. It depends upon the real result here. Anyway, I have taken these numbers. Let's verify this one. What is there? So now I'll execute that one by instruction. Now I'll go to the last instruction. So last instruction is executed, but the flags are not changed because these flags now do not reflect this the meaning of the flags whatever specified here. Now we will verify one by one. Now what I'll do is, so I'll stop my program now for a moment. I will modify the data now. What is the data I'll modify? So I will take the number. So let's say 0, another number also 0. Now what will happen here? I'm adding the two numbers. The answer is 0 now. So I'm explicitly making certain answer to be reflected in my result. That is 0 to be reflected in the answer. So I want to see that whether 0 flag will change or not for that. So now let's say look at this program now. These all 4 are zeros now. I'll execute the program now. So first instruction, second. Now look at it, immediately changed 0 flag. So why it has changed? Because answer produced by this instruction, that is a previous instruction. These flags are always talk about the answer of the previous instruction. For example, you are not executed this instruction, which is a previous instruction add. So these flags always correspond to the latest instruction what you executed. The moment you execute the next instruction, the flag reflect what? The answer of that instruction. So it always talks about the result of the previous instruction. Now, since the answer is 0, 0 is set there. Now, similarly, if I want to, for example, set the sign flag. So sign flag, we know that a 32-bit number, in a 32-bit number, the last bit of the number, that is D31. So if you take a number, so let's say, now I have taken a number. Let's say I have a number now. I want to set the number. Let's say, look at this for a moment. Now, my number is what? D31 is the last bit. Then after that, D30. Then it is D29. Like that, it continues. Then it comes to the D1. Then the next is D0. So how many bits are there in my number? Totally 32-bit number. 32 bits are there. In this 32 bits, the D31 is the last bit. We call it an MSB bit. D31 is called as what? Most significant bit. So D31 is the MSB bit, most significant bit. What is the meaning it carries this bit? So whenever D31 bit is 0, we know that number is what? A positive number. Number is a positive number. Whenever this bit is 1, that means that what does it represent? So it's a negative number. It's a negative number. So that means that. So whenever we used 32-bit number to represent the signed numbers, see, if you are using complete 32-bit numbers to represent only the magnitude, then the whole of the D0 to D32, that is 2 to the power of 32 minus 1. What is the range of the number? 0 to 2 to the power of 32 minus 1. That is a range it's represented by these numbers, by this number, because you represent whole of this number to represent only the magnitude. When I want to represent this 32-bit to represent a signed number, then I cannot use all the 32 bits represent a magnitude, because I'll use only 32 D0 to represent the magnitude. The remaining 1 bit 31 I'm using for to represent what? Sign. In that, what is my range of a number? Minus 2 to the power of 31 minus 31 to plus 2 to the power of 31 minus 1. That means the sense. So this is the range of numbers, because your magnitude is what now? 2 to the power of 31. 2 to the power of 31 minus 1. It is not the 2 to the power of 32 minus 1, because why? The range is reduced. So, but you are giving the range to represent both negative range also, both the positive range also. Of course, the range is reduced, but you are accommodating to represent both the negative numbers also, positive numbers also. So if somebody asks, so what is the range of the numbers? You can always say that it represents negative, then 0, then it represents positive also. That is, so minus 2 to the power of 31, 2, plus 2 to the power of 31 minus 1. So that is the range it represents. You are representing 2 to the power of 31 minus side, and the positive side represent what? 2 to the power of 31 minus 1. So the whole range of numbers you represent here. So whenever you want to do a programs on sign numbers, you should consider that always I'll be using 31 to represent the negative, that is a sign of a number, whether it's a negative or a positive. Am I audible?
Yes, sir.
Yeah. So in such cases, my D31 represents the negative. So whenever you want to see whether the result of a number is negative or not, negative or positive, how do you look at it? People will not look at D31. That is why, to make it easy for the programmer to refer the sign of a number, they provided a flag called sign flag. In this case, sign flag is called as negative flag, N flag. So we will see that. We will modify the bit value of this one by some logic, and we see that it's going to change or not. Now what I'll do is, I'll take some number, move R0, some number I'll be representing here, some number 10 or something. Now what I'm doing is, I'm going to add a number. I'm going to add these two numbers. Before adding, I want to set, set a particular bit in this number. That is the sign flag, I want to set it. So what I'll do is, move R1, R0, then I can able to LSL, logically shift left, hash 31. So let's say I will put this as a 1 to start with. Now what I'm doing is, this we will study in detail probably in the lab session today. So I'm just taking a number 1 to the R0. So what will happen? The last bit of D0, it becomes 1. So after the moment I do this, what will happen? All my zeros, yes or no? The last bit becomes 1. That is in the 32-bit number. So then this number R0, I am pushing it to what? I am to R1. I am putting it this to R1. So whenever I put this into R1, I am doing certain manipulation. What I am doing manipulation? Don't put R0 into R1. You shift the R0 number left direction by 31 times, and then put it here. Whenever I take this number, which is 32-bit number, push the 1, that is shift the number 31 times, means the 1 will come to here, what? This position. So that means that what I'm doing is, I am just creating 1, 0, 0, 0, 0, dot, dot, 0. So since I am rotating this number 31 bit times to the left side, the 1 which was here will come to this position. Once you have this number, that is shifted number, I'll put that number into R1. Effectively, I'm doing this, all this drama circus, only to make sure that the last bit to change in the R1. This is the result. Now I'll put S here. So why I'm putting S here? Because I want to update the flags. So now I'll compile my program. I'll run this one. This program. Now I'll expand the Cpsr register. Now all these flags are now 0, 0 to start with. Now I'll execute the first instruction. R0 is equal to 1. It has become 1. So no flags has changed. Now I'll execute again. Now what will happen? See that N becomes 1. Why N becomes 1? Look at the R1 answer. What is the R1 answer I've written? R1 answer, I've written this answer. That means that 1, 0, 0 is what? 8. And then all are 0, 0. So you can look at that 8, 0, 0, 0, 0 is there. Now, since the last bit is 1 in the result, and you ask the instruction to reflect the flags, that is yes, you have written it, immediately what will happen? The flag becomes 1. So whenever the programmer, after this instruction, go and verify this flag, oh, it is a 1, it has become, then I can take my next step. If logic I can implement. If the number is less than something, the logic you want to implement, what I can do is I can look at this flag, I can write a jump instruction. So the branch instructions with the looking at the flags provide the facility for a programmer to implement if and else logics based on what? Less than, greater than, equal, and all those I can look at it. So now we have seen that in this discussion how the sign flag will work, how the zero flag will be worked. Similarly, the carry flag. How does the carry flag will work? So last 2 minutes, please bear with me now. Now what I'll do is I'll modify this program to something else now. So I'm going to add 2 numbers. So I'll take one more number now. So MOVES R2, I'll take the number. Same thing, I'll write it R0. So LSL hash 31. Now what is the number? Now I have 2 numbers. One number is 1000, other number is also 100. I'm adding these 2 numbers. Whenever you add these two numbers, what is the result you are going to get? So I will add these 2 numbers now. Add S R1 R3 comma R1 plus R2. So now what are the 2 numbers? R1 is nothing but this number. R1 equals this number. R1 equals this number. Now this represents R2, so which is equal to this number. Now what I am doing is, now I am producing an answer of these 2 numbers by adding in R3. R3 equals R1 plus R2. So what I am doing is, so I am adding these 2 numbers and putting in a R3, but also asking for what? Flags to change. So whenever you add these 2 numbers, you know that 0 plus 0, 0, 0, 0, 0, 0, 0, 1 plus 1 becomes what? 0. And then since it's the last bit, carry is generated. So what is the answer of this one? So answer of this is nothing but what? 0, 0, 0. All the numbers are 0, 0, 0. Plus what? Carry is generated. Carry becomes what? 1. Because why? The last bit of the number, whenever you add, if it a bit coming out of that addition, that is called as a carry, as you studied in the computer organization. Let's verify now whether that is reflected in the program or not. So now what I'm doing is I'll execute this program step by step. So I'll run this program step by step. Look at the R1. R1 contains what? 8000. Now I'll execute another instruction. So look at R2. R2 also contains 8080. Now I'm adding these 2 numbers. Add S. Now I'll expand the CPSR at this moment. So now what is the number? N is 1 because why? In the previous instruction, you moved 1 into the last bit. That's why 1. All other bits are 0, 0, including the carry. Look at the carry is 0. Now I'm adding it. So now look at that. The flags have changed. Why these flags have changed? It is based on this instruction. In this instruction, explicitly I've generated a carry. Look at that. Carry is generated. In this, when you add these 2 numbers, answer becomes what? 0. That is why 0 flag is set. In this one, the last bit becomes what? 0. D31 becomes 0. That is why what will happen here. So the 0 flag becomes what? N flag becomes 0. It's a positive. So it's a positive number. Answer is 0, and the carry flag is generated. What about a overflow flag? So overflow flag is used in signed numbers whenever you add 2 numbers and the answer is more than, for example, let's consider an 8-bit number. 8-bit number can store maximum signed number. How much? Minus 128 to plus 127. I'm expanding with reference to an 8-bit number. So whenever you add 2 signed bit number, 8-bit numbers, answer should be what range? Minus 128 to plus 127. Let's say you are adding plus 120 plus 120. Both are positive numbers. Then once the answer is what? Plus 240. Plus 240 you cannot hold in a 8-bit signed number representation because what is the range? Minus 128 to plus 127. But you are added 2 positive numbers which produces a result which is more than plus 127. That is called as overflow. Whenever you add 2 signed numbers, if the signed number magnitude is more than what can be represented by your destination, there is a overflow. In this case, what will happen? 100 is what? Is a signed number. It's a minus maximum. It's a minus 2 to the power of 31 is represented by 100 is nothing but what? Minus 2 to the power of 30. That's a maximum signed number, maximum negative number. It's a maximum negative number. When you are adding 2 maximum negative numbers, no way you can represent that in the 31 bits magnitude. You take an example of, I'm giving example of 8-bit number. Say for example, minus 128 is the maximum number you can represent. Minus 128 is the maximum number you can represent an 8-bit number. When you add minus 128 plus minus 128, you should get what? Minus, so it should be more than 256 you're supposed to get it. But you 256, you cannot represent it. That means that is an error. Similarly here, so you are representing two negative numbers here because both the numbers 88 is what? Negative numbers. It's a maximum negative numbers. If you try to add them and then keep in the answer in R3 register, R3 cannot hold it because why? You produce a negative number which is more than what it can hold. That is why overflow flag is generated. V is equal to 1. So this is the meaning of the 4 flags what we have discussed in detail about this discussion. So this completes about the ARM ISA architecture. So any doubts, you can always raise your doubts.